Hello everyone and welcome to this session where we are going to talk a bit about different starting devices of electric machines. Why would we pick a frequency drive instead of a starter and vice versa. So hope this session will give you a bit background and sort of knowledge that you can discuss stuff like this with our customers. So, what is the difference between a starter and a frequency drive? I hope you have seen some of the other sessions where we describe how the frequency converter works, how it fits into a system, so you have a bit of background on the frequency drive. Because a starter is sometimes referred to as a drive in some specifications, and a drive is sometimes referred to as a frequency drive or a frequency converter. So please be aware of that and have a closer look at what do the customer really need for his application on board the vessel. A starter is a cabinet with some starting equipment inside. Different types of starters do we have, and we have a frequency drive as well, a cabinet. Both of these two are connected to the main switchboard. And again, referring to some of the other sessions, at the switchboard we do have fixed frequency, let's say 60 Hertz for most of the vessels. And again, referring to some of the other sessions, an electric machine, an electric motor is totally dependent on the frequency input. So we can have a motor connected to a frequency drive, or we can have a motor connected to a starter. We have, again in another session, talked about the difference between these, between direct connection of the motor to the switchboard and connection through a frequency drive. Basically, the main difference between these two is that this one has stable 60 Hertz input and stable RPM. Let's indicate 1200 RPM. Maybe 1800, maybe at 50 Hertz, then we would have 1000 RPM. At 60 Hertz we have 1200, and we may have 1500 and a lot of other steps dependent on the frequency input. But let's say this motor is designed and produced for 60 Hertz and 1200 RPM. So this motor, at once it is connected and started up, it will run constantly at 1200 RPM. This motor, however, connected to a frequency drive, will have an input 0 to 60 Hertz and therefore 0 to 1200 RPM. The starting device may be of different technologies. You may have heard dual start, direct online, and it is what it says. It is just a switch that connects your motor direct online. So in fact, no other starting equipment for this motor than a switch, like you're switching on your light in your house. Just a switch, switching the motor on, and then it is running constantly at nominal speed. We have something else we call YD or star delta. That is a starter that gives your motor a bit more smooth start. So star delta start will give your motor a bit smoother start than the direct online. However, at once it has started, after a couple of seconds, then it will be running at fixed speed due to fixed frequency. We may mention auto transformer start, AT starter. It is basically nothing much more than we introduce a transformer just to give the motor a bit smoother start. And we may add soft, which is an expensive starting device. A soft starter will just give you a soft start, but after the start, after the starting sequence, the motor will still run at fixed RPM. Because all these starting devices, all these ways of starting the motor will connect the motor directly to the 60 Hz after the starting sequence. So no matter what or which of these starting devices you pick and choose, your motor will run at fixed RPM throughout all the duty. So just in brackets here, a soft starter is a quite expensive starting device just for bringing your motor up to speed and have a stable frequency and stable RPM. So in many cases you can almost pick a frequency drive instead of a soft start. Or you may choose a less expensive auto transformer start, because that gives you almost the same benefits as the soft start, but cost a lot less. So that's just the different starting methods to start the electric motor. The frequency drive, however, will give you a very smooth start and will give you a smooth ramping up of the RPM of the motor. So the frequency drive will give you a smooth start and full control of the RPM regulation throughout the complete area of RPM you have for this motor. And the beauty by an electric motor controlled this way is that you have constant torque all the way throughout the RPM range. So you have full torque from 0 RPM and all the way to full RPM. So you have a lot of power to start. With this one, you do not have a lot of torque through the start sequence, so you need to be conscious about what equipment you intend to start and look at the complete starting device as a system together with the switchboard, because at once you push the start button on a big motor, you will influence the voltage on the switchboard as well. So the frequency drive works in a totally different way and will give you variable speed. You can regulate freely in between 0 and 1200 RPM. Perhaps I should have mentioned earlier as well that you have the possibility with this one to turn the direction the opposite way. So you could say 1200 through 0 to 1200. So in both directions you have 1200 RPM controllable through the frequency drive. And that is of course something you need when you have a fixed propeller, so you can run the propeller in both directions. For a tunnel thruster, let's say, fixed blades. If you have a winch, you can run the winch in both directions. So just as you are are aware of that as well. Okay, but when you are discussing with a ship owner, and he is not, he doesn't know why he should choose a frequency drive or why he should choose a starter, and he can easily see that the frequency drive is way more expensive than a starter. Well, why would we then choose to have a frequency drive in some applications and not in other applications? Then we need to have a look at the propeller curve. And I'm an electrical guy, so please bear with me. I will try to do my best with a propeller curve. So let me put up a propeller with pitch, and in this diagram, let's say we have a 1 megawatt propeller. So this is a 1 megawatt controllable pitch propeller. The propeller of 1 megawatt will have a curve for the 0 pitch. You may think that a propeller running with 0 pitch do not need much energy. In fact, it does. So let's have power in that direction and RPM in that direction. I would then indicate a 0 pitch curve for this propeller. And for a 1 megawatt CPP, you could in fact at 0 pitch have easily, let's say, 200 kilowatt. 0 pitch, 0 pitch, 200 kilowatt if you have fixed RPM for the propeller. Okay. So, if you have a tunnel thruster that are running with very low or close to zero pitch for many hours, this propeller is running due to the fact that the captain, he would like to have it ready for maneuvering, ready for if he is in DP situations, would like to have this propeller running to be ready to operate momentaneously. And for a fixed speed propeller, as you have here, you have fixed speed. You need to regulate the thrust by regulate the pitch of the propeller. So, okay, fixed speed, we have that speed here. Let's say let's say 200 RPM. Tunnel thruster, maybe 200 RPM, 180. And this propeller has to run at 1200 RPM on the motor, 200 RPM on the propeller, due to the fact that the owner has picked a starter. So the starter gives you no possible opportunity to regulate the RPM. The RPM is fixed. It's fixed on the propeller. So this 1 megawatt controllable pitch propeller running at many hours, maybe at zero pitch or close to zero pitch, you will have 200 kilowatt just to have this propeller running and ready to be used. So for a typical offshore vessel where this propeller is running for hours, many hours every day, this loss of 200 kilowatt, let's say he has several propellers, several tunnel thrusters, maybe 5, so 5 times 200 kilowatt just due to idling around is 1 megawatt in loss. 1 hour is 1 megawatt hour in loss. How do you produce that megawatt hour? You have to produce it by your diesel engines. So obviously this loss for a fixed RPM propeller, it may be quite huge if you're spending a lot of time in low load conditions. So if we then introduce a frequency drive, it will increase the capex for the ship owner. He has to pay for this frequency drive up front. However, the frequency drive will give you the opportunity to reduce the speed from nominal speed and all the way down to zero speed. So with a frequency drive, you can reduce the RPM, and when you reduce the RPM, the kilowatt you need to drive the propeller is dramatically reduced just by taking it down to the half, or even you can take it all the way down to 0 RPM. And even though you take the RPM down to 0, you're still ready to operate, because the drive, the motor, everything is connected it is ready. It is just for the captain to pull the lever, and then this react momentaneously, and your propeller is moving the vessel. So if your ship owner would like to have a starter, however, his operation of the vessel will be many hours with the tunnel thruster in duty, then you should be aware of, okay, let's have a look at this. Maybe we should add a frequency drive instead of a starter, because adding a frequency drive will take away your propeller losses. So the frequency drive itself do not reduce any loss in the electric part. It is in fact opposite. The frequency drive itself will add some losses in the electric system, because it is electrical losses through the frequency drive that you do not have with a starter. However, if you compare the small losses you add with a frequency drive, if you compare that to the losses you have with a propeller and the propeller losses, you will in many cases see that it's of huge value to raise money, utilize what you have as a capex and invest in a frequency drive, and then bring the operational cost down. And this is basically the only reason why we would like to have a frequency drive to a propeller. Because we want to regulate the RPM. That is the reason. We want to regulate the RPM on the propeller. And why do we want to do that? It is to reduce the losses on the propeller side. And of course, when you have the frequency drive, you can as well look into the propeller and see if maybe he can pick a fixed pitch propeller to save from the controllable pitch equipment. However, the optimum, really best solution is to have controllable pitch and controllable RPM. Then you really can optimize your propeller performance to the very best. So that is the optimum solution for reducing operational cost. So that is just some short introduction to the starter equipment and the frequency drive. Why do we choose a starter in some applications, and why do we choose a frequency drive in some applications? Because if you have a cargo vessel, let's say, that are approaching harbor once a week, using the tunnel thruster once a week, just a few hours a week, well, then what he can save isn't really that much. So you have to look into the utilization of the equipment on board, what type of vessel. So if this vessel is a cargo vessel, just spending a few hours per week or maybe several hours per week as well, you have to look into that. Well, then maybe these savings, to save these 200 kilowatt, isn't really a big deal, looking at the investment for a frequency drive. But for a tunnel thruster, a propeller that are in use many hours, um, and a big percentage of the usage is propeller idling or in between 0 and 50% load. Well, then you should start to look at maybe it is good to have the frequency drive. Starter, frequency drive, different types of starting methods, still the same. Fixed RPM is the result for this type of starting device, and the result thereafter for the propeller is you have to stick with fixed RPM on the propeller, then you have losses on the propeller side. Maybe it doesn't matter because you use very little this propeller. Maybe it means a lot if you use it a lot, and you should have a look at a frequency drive. Okay, thank you for today's session.